Hello everyone. In this video, we will continue to discuss topic 9.3, interference. In particular, we will focus in on thin film interference. Thin film interference names a phenomenon that all of you will be familiar with, although perhaps you did not know the name. When a transparent medium forms a thin film, you often see very characteristic color patterns. So for example, oil on water or thin bubbles made of soap usually show this sort of iridescent color pattern. And that's being called, or that is being caused by thin film interference. Thin film interference is defined as the interference between waves reflected or transmitted at multiple boundaries a small distance d apart. To understand the basic idea of this, we'll consider sort of a bubble structure. So a thin layer of some kind of higher index material, and then having that bubble sort of sandwiched between two other layers of lower index material. To consider thin film interference or understand why this is going on, imagine some incident light striking the film at point A. That incident light will be split into two parts. Part of it will be reflected at that first boundary, and then part of it will be continually transmitted. It'll be refracted through the boundary. And then that ray will also undergo both reflection and transmission at point B. So that ray will be split, and part of it will be reflected back, and part of it will be transmitted forward. And then the remainder of the light will at that point be refracted out at point C, parallel to the initially reflected ray from point A. And this is the important part. The interference happens because the first reflection interferes with the second reflection. So the light from the first reflection interferes with the light that was reflected at B and then refracted again at C. To derive the formulas related to this, to understand the phenomenon, we also need to remember one more thing, which is that at each boundary, we need to pay attention to whether or not the second medium has a higher index of refraction than the first. And the reason why is because if the second medium has a higher index of refraction than the first, you will also get an additional phase shift, an additional pi phase shift. So you get an exact inverse of that wave. One more thing is that we are also going to assume that theta is very, very small. So I know that it's not drawn like that on the diagram so that you can see what is going on, but we're going to assume that the incident light we're talking about is more or less straight on. And so the length of AB will be about equal to the length of CB, which will be about equal to the thickness of the thin film D. All right, now we have the tools to find the equations that relate. So the first situation we'll consider is that thin bubble. In particular, we will consider the case where N1 is equal to N3, and both of those indices of refraction are less than N2. So this is the situation of a thin sort of soap film, for example. And that means that at boundary A, because N1 is less than N2, we get an additional phase shift of pi, and at B, however, because N3 is smaller than N2, we do not get the same phase shift. And same for the refracted ray out at point C. So we only get one phase shift here in the three interactions at A, B, and C. To derive the formula, we'll consider constructive interference first. As always, we have constructive interference where an integer number of wavelengths is equal to the path difference, except in this particular case, we'll have an extra pi phase shift, that is equivalent to 1 wavelength divided by 2, so a half wavelength phase shift. As a result, I should mention, we are using the symbol m here to indicate the number of wavelengths because n is already being used to indicate the index of refraction. So we set the path difference originally equal to m lambda, now equal to m plus 1/2 lambda because of the extra phase shift, but that path difference is about equal to 2d, because remember, we're assuming theta is about equal to 0. As a result, 2d is equal to m plus 1/2 times the wavelength. But what is the wavelength? We have to be a little bit careful here. When that light wave goes into the medium 2, into the bubble, remember that it slows down. And when it slows down, the wavelength decreases in that medium. How much does it decrease by? It decreases by exactly a factor of the index of refraction. So if the index of refraction is 1.4, for example, that wavelength will be exactly a factor of 1.4 smaller. Okay, so now we can put it all together and we can say that 2d is equal to m plus 1/2 for a half integer wavelength times the original wavelength of the light divided by the index of refraction. This is written in your data booklet as 2d times n, the index of refraction, equal to m plus 1/2 lambda naught. By a very, very similar argument, you will see that the equation for destructive interference, which still picks up that extra phase shift, is now, with that extra phase shift, an integer number of wavelengths. And so the result is that our traditional equations are reversed. You get constructive interference when 2dn is equal to a half integer of the original wavelength, and you get destructive interference when 2dn is equal to an integer number times the original wavelength. This is for a situation with one phase change, as in the case of a bubble. Now, if you take a look at the thin film interference on a bubble, we still haven't quite explained why you see these bands of colors. And the answer is because the bubble itself is going to have varying thicknesses. And so white light that reflects off the bubble will have different wavelengths at different points undergo constructive interference. And then at other points, you'll see some wavelengths undergo destructive interference. And so you get a very characteristic spectrum where in sort of one of these red bands here, you can see that that red light will be reflected. And so if the original wavelength is amplified in the reflection, that's when the wavelength is undergoing constructive interference. And you also see this sort of greenish blue band here. I'll do my best to sort of point it out, that greenish blue band in between the red bands. That's when you're getting a greenish blue wavelengths amplified in the reflection, so undergoing constructive interference. Whereas the wavelengths that undergo destructive interference will be absorbed. You may want to try this worked example here.